Hello, everybody. My name is Tim Tague. We're going to discuss ESE403 Exam 3, Problem 1. So this problem was about clean air solutions in a city. The company was tasked with reducing their annual emission rates for three different pollutants, particulates, sulfur oxides, and hydrocarbons. And there is a certain amount of million pounds per year that they're supposed to reduce their emissions by. They have multiple ways of reducing emissions for each particulate. Um, and so they have multiple abatement methods to reduce these emissions. And there are obviously annual costs for each different abatement method, um, as well as their numbers that they estimate for how much a reduction of emission rate for each particulate that each that each abatement method will be successful in doing. So we're given these estimates. We're tasked with trying to formulate a linear programming model to find the minimum cost function, um, as well as later on do some sensitivity analysis as to how sensitive some of their estimates are and how important it is to have correct estimates. So for part A, as you can see here, this is problem 1A. We're tasked with formulating a model for this program and solving it. So we have these 6 decision variables that they use. These are their 6 different abatement methods. So for blast furnaces and open hearth furnaces, they have three different things they can try: taller smokestacks, filters, and better fuels. So X1, X3, X5 correspond to blast furnaces. The taller smokestacks, filters, and better fuels. X2, X4, X6 are open hearth furnaces, taller smokestacks, filters, better fuels. So uh, we're minimizing the cost. So we're minimizing X1. They estimate costs $8 million annually. So that'd be taller smokestacks in blast furnaces. X2 costs 10 million annually. So we're minimizing this. These are in millions, subject to some constraints. So the first 3 constraints all relate to how effective the city needs the clean air standards to be. So this first constraint is for particulates. They need that the reduction in annual emission of particulates needs to be 60 million pounds or more. So basically, and X1, which I think I mentioned earlier, was the taller smokestacks and blast furnaces, reduces particulates by 12 million pounds per year. So we need 12 million pounds per year worth of this plus 9 million pounds per year, so on and so forth, needs to be at least 60 million pounds per year for particulates. Constraint 2 here is for the second fuel the second pollutant they want to reduce, which is sulfur oxides. The taller smokestacks and blast furnaces reduces sulfur oxides by 35 million pounds per year, so on and so forth. It needs to be at least 150 million pounds per year. And this third constraint is for hydrocarbons. They need to be reduced by at least 125 million pounds per year. So these are the constraints for each abatement method, how effective they are in reducing hydrocarbons. Lastly, what they did in their estimation was for all the different abatement methods, they had a maximum feasible limit for each abatement method, and that was the value of 1. So the estimates that were given below about how effective things are in reducing emissions were based on how much different abatement methods can reduce emissions when used to their feasible limit. And the feasible limit is represented by a value of 1. So when we run this, we were going to get an optimal solution for each different, how many of each abatement method they should use up to a value of 1, and the total cost for this, which would end up being $32.155 million. In Part B, we are then asked to ignore the constraints with no uncertainty about the parameters, which is the constraints limiting values to be less than or equal to 1. So this will help us identify which of the parameters are more sensitive. So as you can see here, we just take out the constraints C4 through C9 from problem A. And in problem B, we run this. It's the same cost function. When we run problem B, you'll see that they only end up using abatement method X2 and X4, which are, let me double check my notes, X2 and X4, which are both related to open hearth furnaces, the taller smokestacks, and filters. So this kind of implies that x2 and x4 would be the most sensitive parameters and should be estimated more closely. They're more important to estimate correctly. When we move on to part C, what we were tasked with in part C were two separate things. First, we were asked to, so I guess backtracking a little, they estimated the cost for each abatement method, and it said that they could be off by a lot in this estimation. So part C, we were looking to see how much, if the true value was 10% less and 10% more than the estimated value of the cost, how much would this alter the optimal solution? So let's run the 10% less. So if you remember, the original optimal solution cost $32.155 million. If the cost of each abatement method was 10% less than they estimated, you'll see this drops to $28.939 million. And you still use the same amount of each abatement method, but obviously the cost drops pretty drastically. And if the cost were per se 10% more, so originally it was 32.155 million, you're now up to 35.37 million. And so obviously for the 10% more, I just multiplied by 1.1, each of the costs, 10% less multiplied by 0.9, pretty straightforward. So obviously the cost is very important to estimate, and a 10% change in cost can, in either direction, can result in a massive change in your most efficient cost. Moving on to part D, we were asked to convert the minimization problem to a maximization problem. This is pretty straightforward. The only thing that you do is, it's maximization instead of a minimization. It's the same cost function, but instead of greater than or equal to signs, you have less than or equal to signs. It's pretty straightforward to do. Let's run this as well, just so we can get the value. So when we convert to a maximization, we get a cost of 34.303 million. And then from this maximization, we're asked to develop the dual problem from this maximization problem. So here's the dual problem you will see. So basically, yeah, just developing the dual problem like we've learned throughout the year. Can explain it. I guess it's more in the written work. So let's just run this for the dual problem. Again, this is built off of the primal maximization we just made in the last step, the dual of this. As you can see, the dual of the maximization is the minimization. And we are going to get an objective value of 34.351 million. There's your Y1, Y2, Y3 values. Now, if we were to make a dual problem from the original minimization problem, it would be a maximization dual problem. And obviously the signs of the constraints would then be less than or equal to constraints. So that is pretty much all I have for problem one. I didn't get much farther. I know it's extra credit now, so I didn't get much farther, but I wanted to just create that and share. So I'll stop recording now, and thank you.